So welcome everybody to this new edition of Virtual Time Series seminars. Our first speaker is Marcelo Fernandes from São Paulo School of Economics. And as a kind guest panelist, we have Abdelaati Dalouia from Toulouse School of Economics. Thank you very much both for being here. So Marcelo, the floor is yours. Thanks a lot.
Thank you very much. I'm sorry for the technical problems and thank you for the invite. So today I'm going to talk a little bit about estimation risk and conditional expectiles, and this is joint work with Victor Henriquez, who is a former PhD student of mine, and Duda Mendes, who is also at São Paulo School of Economics. So I guess a couple of you have already seen this presentation, especially Abdelaati, and so I'm sorry for that, and for asking Alessandra to invite you as a guest panelist. But anyway, so I guess it's a topic that you really enjoy. So hope I changed a little bit the presentation to make it a little bit funner for you. Anyway, so where do we start? We start about, how we want to measure downside risk. And obviously there are guidelines there, for regulatory reasons. And the Basel Accords used to say that you should do that, right in the beginning. But then there were a lot of backslash, especially after the crisis in 2008, because we all know that valid risk does not recognize diversification gains. It depends only on the magnitude of the tail event, and because of other reasons as well, people were using severely misspecified models, with Gaussian errors, and then obviously the valid risk was not giving a good picture of the kind of risk that banks were involved. So after the 2008-2009 crisis, Basel starts saying that perhaps we should move to expected shortfall. Expected shortfall is essentially the conditional expectation of the loss distribution given that you exceeded the valid risk, so a given quantile. And, it makes sense because it's going to protect you against more severe losses and everything. The problem with expect shortfall is that in some sense, it's not a listable. It's only joint listable with the valid risk. And so it's a little bit more difficult to backtest as compared to valid risk, as an individual risk measure. But that's not the main problem. The main issue is that it's very hard to estimate, like the conditional expectations on the tail. It's pretty difficult to do that. And this obviously is going to lead to very harsh capital requirements, but also, and that's what I think it's most troublesome, very imprecise ones as well, because as it's hard to estimate, like the bands that you're going to get, the confidence bands are going to be very large as well. And if you're dealing with very extremely volatile markets and where, the tail events are frequent and severe, like for instance in the crypto markets, that could be a very bad measure of risk, like at least to rely on if you want to compute the capital requirements. So what we're going to do in this paper is to look at these alternative asymmetric least square based risk measures. Today I'm going to talk only about expectiles, but we have also a paper on extra miles as well. And extra miles are pretty interesting because they satisfy most of the risk properties that we would like a risk measure to satisfy. So they are law invariant, they're coherent, and they're listable. By the way, they are the only listable coherent risk measure out there. And obviously they depend not only on the probability of the event, like the quantile, but also on how severe the event can happen to be as well. So, the tail loss. What we're going to do is essentially to establish a methodology to predict expectiles. So we want to estimate conditional expectiles, and we want to understand what is going to be tomorrow's conditional expectile given conditional on the information we have today, right? And we're going to empirically assess that, in the crypto markets and see how it looks like, once compared with expect shortfall and valid risk, okay? So let me give you a quick primer on asymmetric least square based risk measures. expectiles were developed by Nguyen and Paolo in this econometric 87 paper, and they were not really envisioning these applications to risk measures, but it was just in a way of putting together an estimator that had the properties of least square estimators, but with a loss function that would be asymmetric. And then Abdelaati and co-authors, they pick it up in the 10 years ago, more or less. Then they start writing a series of papers and establishing the syntactic theory and all sorts of interesting things about expectiles. Before introducing what expectile is, for those who don't know, I would like to start with the valid risk measure, which is essentially a quantile, right? So QT here is just a quantile, is the argument that minimizes this expectation of this check function here, the usual quantile check function. And obviously this quantile check function is non-differentiable. And in the literature of quantile estimation, there are a whole bunch of papers, trying to deal with that. Obviously, you can estimate, non-differentiable functions without any problem, but Horowitz, for instance, have shown, that perhaps what you should do is to smooth this function. So instead of using the indicator function there, the indicator function of y being lesser than theta, what he does is to use some kind of a smoother function there. And in a recent paper with Emmanuel Guerre and Eduardo Horta, have a paper where we smooth the whole objective function to estimate the quantile regressions, and we show that it has some refinements in terms of asymptotic theory. So quantiles are great. Now we all know that they completely characterize the distribution. They're robust to outliers. They are easy to backtest because of elicitability. But as we know as well, in terms of risk measure, developed risk does not recognize diversification gains. And if you are interested in adding cryptocurrencies to your portfolio, that's exactly what you are interested in this very low correlation between cryptocurrency and traditional asset classes. So it makes no sense to start using a risk measure that does not recognize diversification gains, at least for crypto markets. So what the main idea here is to tweak this check function, so the quantile check function, so as to get closer to expectations, because in expect shortfall, that's an expectation, and we know that the expectations will satisfy subadditivity property, and hence they are going to take benefit of diversification gains and recognize diversification principle. So that's the check function we're going to use for the expectile. Instead of having, the absolute deviation between y and theta, we're going to use the least square deviation between them. And once you do that, that's exactly what Nguyen and Paolo do. Things get a little bit easier because you get you solve most of the problems of non-differentiability that you get with the quantile check function. It's the least square analog of quantiles, the expectiles. So if you take your level here, tau, which is to half, what you get is just expectation, right? Because then it becomes symmetric and it coincides with the least square, the usual least square loss function. And then what you recover is exactly the expectation of the distribution. Expectiles are going to offer a complete characterization distribution just like quantiles, so it has the kind of properties that we are interested in, statistically or probabilistically. Once you translate that into finance, as for the corresponding risk measure, now you're going to get expectiles depending on both magnitude and the probability of tail events. They account for the diversification gains, and they're going to be straightforward to backtest as well. In fact, as I said before, they are the only elicitable coherence risk measure that we know so far. And an add-on, like a plus for the expectiles is because they have this very intimate connection with the gain-loss ratios. So if you compute this omega ratio, this gain-loss ratio, that looks like what is your expected gain with respect to your expected loss, right? It's essentially going to be and you and you do that with respect to the expectile at a level tau, it's going to be a constant function of tau. So you kind of fix. Once you have a expectile, you know exactly what kind of gain-loss ratio we're talking about. So you're fixing your gain-loss ratio. And this is going to play a role later on when we look into crypto markets and the application. So as I said, the talk today is about how to estimate conditional risk measures and how to predict them in the next period. So obviously, if we want to learn about the risk tomorrow, give information today, now we have to start with a link between today's and tomorrow's distribution, right? And we're going to do that with a conditional location scale model. It's a traditional way to do in financial econometrics. It's not the only way to do. We could set up straight away expectile regression. A couple of papers have been doing that in the past. Gerard and co-authors, and there's a recent paper in Journal of Financial Econometrics. But we want to keep it mostly like plain vanilla financial econometrics. Location scale model is something that we know how to deal with, and we thought would be a nice way to start, and a nice starting point. So once we have a location scale model, then we can estimate it by quasi-maximum likelihood. And we just assume that in the innovation process, E here comes from we treat it as if it comes from a Gaussian. We estimate if that's the case, or could be something else. If you're using exponential Garch, for instance, it would be a different distribution. But you could easily estimate by quasi-maximum likelihood both the conditional mean and the conditional variance. Once we do that, then we can compute what are the standardized residuals. So the estimates for this innovation here. So the standardized residuals would be this E hat. And once we take that, we might think about, well, now that we know we have an estimate of the distribution of the standardized residuals, we can talk about the unconditional expectile of the distribution of the true innovation E here. So psi E here is just the asymmetrically square-based risk measure that you're interested in. In this case here, today's talk is going to be the expectile. Once we do that, we can estimate the conditional expectile. We know that in the conditional location model, this is just going to be the conditional mean that I expect from the next period minus the volatility that I expect for the next period given the information today times the unconditional estimate of the expectile. Okay. Now, the last step, obviously, is to assess the estimation uncertainty. The paper is about estimation risk, so we have to understand what is the uncertainty here. And if you want to understand that, then essentially what you have to do is to examine the contribution of each one of those estimation steps to the overall uncertainty in the estimation. So we have to understand how the estimation, in the first step of the conditional mean and the conditional variance is going to affect the estimation in the second step of the unconditional expectile of the innovation distribution. So just to anticipate what our main results, our syntactic theory says that under correct parametric specification of the model, we consistently estimate both the conditional mean and conditional variance. Obviously, this is not new. Then we can get a consistent non-parametric estimation of the distribution of the innovation. We can do that with empirical distribution or with a kernel, kernel estimator. It doesn't matter. Then we can consistently estimate the conditional expectile, but the first step estimation of the conditional mean and the conditional variance is going to affect the amount of uncertainty in the last step estimation. We have a closed form solution for the asymptotic variance. We know exactly how this first step estimation affects the uncertainty in the last estimation step. And we also show that the simple bootstrap procedure that Cavalieri and co-authors and Beutner and co-authors have been working on, called fixed design bootstrap, is going to give us asymptotic valid confidence intervals for our estimates. We also have a second, well, actually a third paper. The second paper is about extremiles. We have a third paper about misspecification, and this is probably the one that it's most incipient out of the three of them. It's under misspecification, what happens is that the first step estimation is not only going to affect the asymptotic variance of the conditional expectile estimator, but it's also going to affect its asymptotic mean. So we have a bias. And we show that, at least in simulations, the theory is not worked out yet. At least in simulations, we show that a double bootstrap procedure helps a lot. It mitigates a lot of these of the asymptotic bias and kind of recovers asymptotic valid, but at least looks like asymptotic valid confidence intervals. I'm going to talk very little about that. Once I show the Monte Carlo simulations, I can comment on how it looks like under misspecification. So let me give you the asymptotic theory right away. And let me start again, like looking at the literature. So this is how you estimate an unconditional expectile. You just do it's like a z-estimator, you just have to look for the argmean of this check function, the expectile check function here. So if you have a fixed level tau, so if you fix the tau here and you want just to estimate these expectiles, there's a whole bunch of papers apart from you, West in 87. There's this paper by Hosman and Claw in Electronic Journal of Statistics, another one by Krashmer and Zal in Scandinavian Journal of Statistics in the year after. And they show how to do that, all the asymptotic theory. So there is not much to be done there. Then Abdelaati has been working with his co-authors on extreme expectiles. It's really interesting literature. And there, instead of a fixed level tau, you have, they are interested in a tau that depends on the sample size. And as the sample size grows, this tau n is going to converge to 1. And they have a whole bunch of papers on that, on how to deal with extreme expectiles, how to estimate extreme expectiles, how to do also do inference. And they also have a paper, Girard and co-authors in nanostatistics for how to estimate extreme expectiles, so conditional extreme expectiles in heavy-tailed heteroscedastic regressions. It's a really nice paper, but it doesn't help us much, right? If you look at this literature, there's not much about estimation risk, because this paper by Girard and co-authors, obviously, as they are looking at conditional extreme expectiles, they want to assess estimation risk. But in their case, it's not really an issue, because for the estimation of extreme expectiles, it converges at a slower rate than the estimation of the regression. This, as tau n converges to 1, as n converges to infinity, the rate of convergence here is not going to be square root of n, but it's going to be square root of n 1 minus tau n. So the first step estimation error, as it's square root of n, is not going to affect the second step estimation because of this lower rate of convergence. So there's no issue there in terms of estimation risk. Now, as for bootstrap methods, Krashner and Zal have a paper on bootstrap method. They speak a little bit about bootstrap methods, but their results are not going to help us much, because first, it's only for unconditional expectiles, whereas we are interested in conditional expectiles, and second, because I think they have an IID set up, whereas we have a time series set up. Okay, so some technical details. I'm not going to go too much into them. It's more or less the assumptions that you expect in any financial econometrics paper. So we have a conditional location scale model, and that we assume that we have correct specification, and then we have a compact support. It's a technical regularity condition that we could, I'm not going to say easily relax, but it tediously relax. We need strict stationarity. We need some geometric strong mixing solutions as well for our process. Then we have some conditions on the volatility process. It has to be measurable, twice differentiable, has to be positive almost surely, and has to be, deification has to be there. And, more or less the kind of things you would expect. And it has to be finite. It has to converge to some finite moments for s greater than 0. And finally, we have some assumptions on the innovation process. It's IID. This could be easy. This is more easily than tediously relaxed. So it's pretty simple to do that. F here is just the distribution that innovation comes, just need to be continuous and strictly positive density with some kind of tail or moment conditions. And then you have technical regularity conditions for, approximation, non-degeneracy, monotonicity, and scaling conditions that are going to appear in this literature, and it's essentially technical. Then we have a series of technical results in the paper. We have two lemmatas. One is essentially, revisiting the usual QML consistency and symptotic normality that we have in the literature. And the second one is a way to deal with initial conditions. There are several ways to deal with that. Franck Sakoya, they have a very nice, well, when they do that, this is exactly the same kind of approach for valid risk. They have a way to deal with initial conditions, and we kind of do something similar, but we have to do with using more general results because of our setup. And then we use this L-key near epoch dependence. Lorenzo Trapani have a couple of papers as well using different ways, how to deal with these initial conditions. They all could be used here for some reason, perhaps of, quirky reason. Duda prefer to use near epoch dependence, so that's why we're using it. But, that's not something that is restrictive or, like in the sense that we really need near epoch dependence. But anyway, that's how we do it. Then the proposition 1 essentially established that the supreme of the volatility process and up to a second order derivative is also going to be near epoch dependence. And then the theorems are going to follow up after that, essentially showing that our conditional expectile estimator is going to be consistent, and the asymptotic normality for the estimator. So let me give you very quickly a sketch of the proof. So essentially, we consider a z estimator. Essentially, our objective function is just the sample mean of the expectile check function evaluated at the standardized residual. The true one is just expectation of that using the true expectile here and the true parameters theta. The first step is to obviously comes from lemmata 1 is to say that 1 and 2 is to say that our QML estimator for the conditional mean and conditional variance parameter is going to be consistent, and then we can estimate the conditional the unconditional expectile of the innovation distribution by the unconditional expectile of the standardized residuals in the empirical distribution of the standardized residuals. So once we do that, then we rely on stochastic equicontinuity of the objective function, which we can easily show, and then we do approximations such as that. Like we look at how much of a mistake we do once we consider the empirical objective function as compared to the objective function, the true one with the true expectations, in a vicinity of the true unconditional expectile xi. So this xi here has to be close to the conditional expectile, so to the unconditional expectile xp tal, and then I have that not only on the true parameters, theta naught, but also on the, so I take the diff in some sense, right? Of this evaluated at the estimate, that's the QML estimate here. And we can show that this only depends on how close the theta hat is from theta naught. Then we can do the similar kind of expansion for the objective function evaluated at our estimate of the conditional, of the unconditional expectile. We show that this is also going to depend on how far away we are from the true expectile. And then finally, we do for the same thing, but now also including the estimation of the theta hat, of the theta naught, using the theta hat, and that this is going to depend on the distance between theta hat and theta naught, and we put all together for a central limit theorem that is going to look at the joint asymptotic distribution of both the conditional mean and volatility parameters and the unconditional expectile of the innovation distribution. So if you have a conditional mean equal to 0, just to make it easier, similarly to Franck and Zakoyan, they have a couple of papers looking at valid risk and expect shortfall. What we find is that this our estimator of the conditional expectile will converge jointly with the QML estimators of the conditional mean and variance parameters to these two normal distributions here. They have some covariance. The covariance, we have a closed form solution for that. And both Z's here are going to be standard normal with their own covariances as well. And then finally, our theorem essentially says that, our unconditional expectile is going to converge to the true one. Even if we do not observe the innovations, that we're essentially replacing them by the standardized residuals, and the normal distribution that is going to convert to which it's going to converge will have two pieces. One is essentially due to the estimation of the expectiles. That's what you would get if you were estimating using only the true innovations. But as we are using the standardized residuals, we get this extra piece here that essentially relates to the estimation of the parameters of the conditional mean and the conditional variance. And then we have closed form solutions for that, for all these quantities here. I told you that we have also a simple bootstrap. So essentially what we're going to use is a fixed design bootstrap. Giuseppe Cavalieri and Coffers have proposed that in a Journal of Time Series Analysis paper, I think from 2018. And then Beutner in a recent paper with some co-authors in the Journal of Econometrics, they essentially use this fixed design bootstrap for valid risk and expect shortfall risk measures. So we thought it would be the easiest way to, the most natural way to start looking at bootstrap-based confidence intervals for our estimator. And actually, we have Monte Carlo simulations for recursive design, fixed design, and all sorts of designs for the bootstrap. They all work. But the theory, the asymptotic theory in the paper is essentially only for fixed design bootstrap. How it works, it's essentially how any bootstrap works. The only difference is here on this on the volatility that we're going to use, that instead, even though we condition on the quasi-maximum likelihood estimator of the conditional mean and conditional variance parameters, we always use the true values of the returns when computing this volatility. And that's why it's called fixed design. So it's not that in the recursive design that normally we would use, we would draw independent samples of the innovations, and then we would reform the returns, always using the previous returns as estimated by this data. That we don't do that. We just fix where everything is conditional on the sample we have of returns, and the volatility process, even though we use the the QML estimators here we plug in the QML estimator, the volatility parameters here, we're always going to use the original returns. And that's how the fixed design works. It's kind of mind-blowing, you know, in the beginning, I had problems, you know, thinking why this would work. Giuseppe couldn't explain me well enough. You know, I had problems and problems until like we sat down to do the theory, and then we realized why it works, and it's kind of magical, you know, like the trick why it works. Anyway, so our syntactic theory, it's not only is going to handle non-differentiability because of the check function, so it's different from what Beutner does, but it also allows for more general DGPs. We don't do a specific Garch model or something like that. It can be any conditional mean location model as long as it satisfies a couple of you know, near epoch dependence structure that we consider here in the paper. And then obviously you get a syntactic valid. We don't know about any second order refinements, but we still get a asymptotic valid confidence intervals using this bootstrap. So let me show you some simulations. Let me spend like 10 minutes here. The design is just like the paper by Christofferson and Silvia Gonçalves in Journal of Risk. And it's a paper looking at valid risk, and I think only valid risk. So we do exactly the same kind of DGPs. We have daily returns from a Garch 1-1 process. Innovations are either Gaussian or student T. As I speak, we have simulations running now with different specifications, but you know, like the Gaussian here is essentially a student T with 100 degrees of freedom. Now we're simulating a true Gaussian distribution, but I guess results are going to be the same. The student T errors here are going to have 8 degrees of freedom. So we have up to 8 moments. We are running with 4 degrees of freedom just to see what happens when we decrease the number of moments we have. We have both moderate and high persistence cases. So moderate, I mean, in a Garch 1-1, we have alpha plus beta equal to 0.9. High persistence is 0.99. Then we have 10,000 sample paths that we simulate in every replication. And then we burn the first 1,000 and then start collecting these sample sizes of 500 up to 5,000, okay? So this 10,000 sample facet, these are the 10,000 replications of the Monte Carlo. What the simulation show, just anticipate the results before showing you one of these big tables that it's difficult to track down what's going on. Well, essentially that everything works beautifully. There is no bias whatsoever, you know, in the fact that we are estimating standardized residuals not affecting the second step estimation of the unconditional expectiles, and we're going to get conditional expectiles that, you know, they're very close to the true ones. And what we also see is that the bootstrap prediction intervals are way tighter than the asymptotic prediction intervals. And not only that, they're way tighter as well than the valid risk and expect shortfall prediction intervals. And this is especially the case for heavy tail distributions. So with the length of the interval is really small as compared to the other ones. So I can show you bootstrap-based 90% and 95% prediction intervals. We have both. For 95 is a little bit better, the results. So I opted to show you the worst results. So here's the fixed design residual bootstrap with 999 artificial bootstrap samples, which once we add the original sample gets 1,000. All the prediction intervals here are based on equal tail percentile method. Again, this is just to be conservative because symmetric intervals work best at 1% and 5%, but we kept everything with equal tail because that's what people normally do. Relative results are very similar across sample size. It doesn't change much. And essentially, if you go for tau to 1%, this is all for tau equal to 5%. you're going to see the expect shortfall and valid risk prediction intervals are going to deteriorate a lot. So I opted to show you the best of the worlds for expect shortfall and valid risk, okay? So here's the benchmark case with alpha plus beta is equal to 0.9. Not sure why I call that benchmark, given that most of the time it's above 0.95. And the high persistence is alpha plus beta equal to 0.99, okay? So if you look at valid risk looks okay in terms of prediction interval. It missed out like 5.15 in the lower end of the interval, 5.95 to above. So the entire coverage is about 88.91, and it has a length of 0.35. So it's doing okay. Once you move to heavy-tailed innovations with T8, then, you know, it gets a little bit worse, but not so much. Coverage is still pretty good, 88.58, but length increased a little bit, obviously, because now you have heavy tails. If you move to expect shortfall, things get a little bit crazier. You know, like, first of all, it becomes a little bit asymmetrical. Perhaps that's why the symmetric intervals doesn't work so well. If you're using, that's why the symmetric interval will work a little bit better instead of the equal-tail percentile methods. Because when you look at expect shortfall, you see that it's rejecting less here at the lower end and rejecting more than often. You know, instead of 5%, it's rejecting 8.225% in the upper side. So the total coverage is 87, still reasonable. Length is a little bit larger. From 35, it comes to 0.40. But once you move to heavy-tailed innovations, now hell breaks loose, and expect shortfall gets really tricky to get good coverage. So coverage reduces a lot to 80%, especially because at the lower end here, you get 18% of rejection frequency instead of 5%. And the length of the interval becomes really large. So you have very imprecise estimates of the expect shortfall. Once you look at expectiles, it kind of nails down beautifully both the lower end, upper end is a little bit rejecting a little bit too often, but still coverage is about 89% in both cases, regardless of how thick is the tail in some sense. And the length of this interval, this confidence interval, is going to be smaller than the ones that we get for the valid risk and for the expect shortfall. Once we move to high persistency, things don't change much. It's exactly as it were before. Coverage reduces by 1% or something like that. The length of interval gets a little bit tighter because as the volatility process is more persistent now, it gets a little bit easier to estimate this, and the length of this confidence intervals reduce slightly. But as you can see, it's pretty patent, pretty apparent that the prediction intervals for the expectiles they are tighter and they work a little bit better than the ones in for valid risk, and especially for expect shortfalls in whenever you have thick tails. Now, what happens under misspecification? Because we knew the model, so we were estimating the correct model. So now what we're going to do is to examine what happens in two cases. The first case is that we miss out, persistence some way, right? So we're estimating a gauge 1.1, but the model is actually arch 2, or it's a gauge 2.2, right? And the second scenario is when we miss out some leverage effect. We estimate a gauge 1.1, which is pretty symmetrical. There is a news impact response, which is symmetric. And what we have now is essentially a symmetric response to positive and negative returns, either through a threshold gauge or through a Gloston, Jagannath, and Runkle gauge model. And just to give you a very quick summary of what the table is telling you is that you can miss out persistency and it's not going to trouble you so much. But if you miss out any kind of leverage effect, then you're essentially screwed. Like the coverage gets really, really bad. Okay. If you do double bootstrap, double bootstrap, all this leverage, we do a double bootstrap trying to pivot the statistic in such a way that you get a little bit more of robustness with respect to this asymmetry. And then what happens is that instead of having 50% of coverage with when you miss out leverage effects, you start having about 80 to 86, I think 81 to 86% of coverage. So it gets way better. But as I said before, we don't have the theory yet, so I will refrain to talk much about that. Okay, so in the last 5 minutes, or 5 or 10 minutes, let me talk a little bit about the tail risk in crypto markets. To be very honest, when Victor Henrique was doing his PhD, I got this grant from Ripple, and we had to do something with cryptocurrencies, and then I just asked him, so why don't you do that cryptocurrency? And that's how it started. And actually, I've realized that was a very fortunate choice, because it's exactly the kind of market where expectiles should play an interesting role, or externalize or whatever. So the externalized facts here is that these are essentially extremely volatile markets with severe, like crashes and things like that. So head tails are huge, and also you have severe jumps upwards as well, right? So you have these huge head tails. So if you want to estimate expect shortfalls, like that's, good luck with that. It's going to be extremely imprecise measures. And if you are a traditional house, and you're now trying to figure out, how you're going to include cryptocurrencies in your portfolio to diversify risks, again, valid risk is not going to be a great measure of risk. And you still have to report to Basel, expect shortfall is not going to help you either. So it's kind of a conundrum if you want to include cryptocurrencies in your portfolio, and you have to agree with all the valid risk and expect shortfall capital requirements. So what we're going to do is to use this expectile to try to understand what kind of margin requirement it would require. So data description, we took data from Yahoo. I know, not great, but we have checked recently with other data providers, and Gustavo Schwenkler have a nice paper on data on cryptocurrencies showing that they are not really great. So you have to combine all sorts of data sets to get a more reliable data set. And if you do that, it doesn't change much the results. So we have Bitcoin, Ethereum, Binance Coin, and Cardano. These are the 4 cryptocurrencies we look at. And, just to have an idea of how they are behaving with respect to more traditional assets, we have SP 500 equity index, SPX, and we have euro-dollar exchange rate. As all these cryptos are currencies, we thought it would be more interesting to compare that to an exchange rate. So the data comes from January 2016 to December 2023. For Binance Coin Cardano, I guess it starts says from November 2017. So we start with MA2 Glaston Junko Runco Garch 1-1 model. We just didn't want to misspecify the model. We don't expect, normally, for instance, the euro-dollar exchange rate, we know it's symmetrical. It doesn't have any kind of leverage effect. The SP 500 would have some kind of leverage effect. So just to be on the safe side, we start with this general model that we estimate. Obviously, we did a couple of robustness checks. The results don't change much if we tweak a little bit the models, as long as the innovations are the standardized residuals are congruent. If we use a ARMA 1-1 or MA2 Glaston Junko Runkel model or eGarch, it doesn't make much of a difference in terms of results. So these are how these traditional asset classes are so different from cryptocurrencies. These are historical drawdowns from 2018 to 2023. This is Cardano. Cardano kind of became dust at a certain point. So you see that these huge drawdowns here, whereas these two guys here, essentially exchange rate, the euro dollar, and this SP 500. So you have way less, the drawdowns are way smaller, right? Whereas this cryptocurrency is very, very chaotic here. It's a big emotional ride for those trading with that because of this huge drawdown. So they're extremely different, right? Now, once you estimate these conditional risk measures, like this is with a rolling window of 1,000 time series observations, expect shortfall, we get obviously is always going to be in magnitude larger than the developed risk, given that is how much I expect to lose, given that I exceeded the developed risk loss. And what we get here for the expectiles is going to be a smaller value. And this happens because in some sense, it was a silly mistake we did, like obviously once you fix the alpha that you're using for the developed risk and for the expect shortfall, the corresponding expectile with the same alpha is always going to give you a lower number than the developed risk. But and perhaps that's not the right way of doing. You should perhaps look at what is the tau that corresponds to that alpha, and I'm going to show you later what gives you that. And this is how it works for Cardano. I never know which one is which. I think this is the Binance coin, Bitcoin, and Ethereum. It's more or less what you get. So this is how they look like if you want, and that's why you should be comparing these guys at the same alpha, is because for a var alpha, I can find what is the corresponding expectile level tau that will give you that same var. And you can see that the expectile is always going to be below the quantile and the expectile, the expect shortfall. And that's why you get this red line always, in the upper, above the green and the blue here. So another way to see that is to look at what is the gain-loss ratio given the fixed capital requirement. So I fixed the capital requirement using the VAR or using alpha, I fix alpha, and I try to understand what is going to be the resulting gain-loss for those assets. So this is for the Bitcoin. As you can see, like the scale here goes from 200 to 500. It changes a lot. There is a huge jump here by the end of 2022, and there's a jump in the Bitcoin prices here. Whereas for the SP 500 is pretty stable. It's always between 200 and 300 more or less. So like it's not really comparable. Like it seems that as you have lots of you have these big jumps in Bitcoins, both to the positive side to the negative side as compared to SP 500. Like the gain loss ratios are extremely different. Like this is more symmetric here, like everything is kind of stable, whereas for these guys, there's some huge upside risks as compared to downside risks that sometimes you're not looking at. So you could do exactly the opposite. So you take the capital requirement as a function of the fixed gain-loss ratio. So what this means is that I'm fixing the tau in the expectile, and instead of computing the tau, instead of computing tau as a function of alpha, now I'm computing alpha as a function of tau. So I fix my capital gain, my gain-loss ratio, and then I vary the alpha that I will have in each period. And once I do that, the alpha here is way more stable, as compared to what we had before. And now the Bitcoins becomes comparable to the SP 500. This works for every asset in the sample, essentially because once we control for the conditional mean and conditional volatility, once we look at the expectiles of all these asset returns, they are all about 2. So that's a question I got in the Ripple conference that someone asked me. Are these assets intrinsically different? Yes, they are, because they have conditional means and conditional variance that are extremely different. But in terms of innovation, the innovation is very similar. They have more or less the same expectile. Actually, this SP 500 has one of the largest unconditional expectiles at 2.05 Cardano has the highest at 2.16, I think. Yeah. Oh, no, 2.08. And the lowest expectile is 1.98, is from one of the, I think it's from Bitcoin. So they all have similar expectiles, this innovation, the innovation distributions for the different assets. And that's why you get, very stable results once you fix the gain capital, the gain loss ratio instead of fixing capital requirements. So let me wrap up in this last minute. What we do is essentially to follow what the literature has been doing for valid risk and expect shortfall. So Christian Franc and Jean-Michel Zakoyan have a couple of papers on how estimation risk affects valid risk and expect shortfall. Once you estimate conditional mean and conditional variance in the first step, we do exactly the same thing for conditional expectiles. Obviously, the technical details are very different due to the non-differentiability of these guys. But, in some sense, it's going to follow similar steps to the ones in Franc and Zakoyan. So the first step estimation is always going to affect the asymptotic distribution. It affects the variance under correct specification. Under misspecification, it affects both the asymptotic mean and the asymptotic variance. We have a closed form solution for the asymptotic covariance matrix under, obviously, correct specification. And we also show that bootstrap-based prediction intervals are going to be asymptotic valid, and through Monte-Carlo simulations that it worked best in practice as well in finite samples. We have this empirical application to crypto markets where I think it's pretty convenient to use expectiles. In the other paper, we show that extremiles, Abdelaati babies, work even better. But so I want to focus just on expectiles today. What is next? We have to finish, if we're able to, the double bootstrap asymptotic theory. And we have to wrap up also the paper on conditional extremiles, which is almost ready. We just had to iron out a couple of technical details. And that's it. Thank you.
Thank you very much, Marcelo. Let me stop the recording first.